All right. All right, we are on. We are cooking. All right, now, is there like a free lunch being given somewhere? All of a sudden, 4 people just left. Is everything all right? Where are you going, Linda? All right, make it quick, please. Okay, thank you. So, I'm asking you, what is the depth? We're looking at water. We're looking at liquids. What are some properties of liquids? We're looking at the nature of liquids. That's where we're starting. I think section 2, is that correct? What is the pressure down here? What is it dependent upon? Okay, is it dependent upon the cross-sectional area? Is it dependent on the cross-sectional area? In other words, if I have this fish, right? Now, that fish is in that container. Okay? Yes? All right, now, let's make a different container, like this. Okay? Same volume. Okay? So are those fish, Alec, thank you for paying attention and being cooperative. It means a lot to me. Excellent. Okay? This fish, are both of those fishies, are they under the same pressure, or is this one under more pressure? Which one has more pressure? A or B relative to the fish? Fish, fish. Alec. A has more pressure. So the fish on A is more affected by pressure than B. Nora. B has more pressure, larger volume. Larger area, okay? Larger area means more volume, yeah. Excellent. Anyone else? Yes, Gabby.
Just adding on to Nora, like the surface is larger, so then there's more.
Okay, understood. Okay, good. The answer is they're equal. Because pressure is only dependent upon the nature of the liquid, gravity, and the height of the column. I would never yell at you. Well, depending upon your perspective, of course. Yes, Victoria. Excuse me. Thank you very much for paying attention. Yes?
So the only part that counts is the part that's like being the fish is like affected by it?
Yeah, the height. Just the height of the column. The height, the depth. If you're at the bottom of a bathtub 1 mile deep, or you're at the bottom of Lake Baikal in Siberia, same. Unless your elevation is a little different, then, but yeah, essentially, yes, correct. Yes, okay? And this is why. I'm going to show you, instead of like proving all this kind of stuff, I'm just going to kind of give you some stuff. I'm going to kind of half-proof things, just to give you a little bit of an idea, okay? Well, if I say to you, we know what pressure is, right? Pressure equals force over area. Wouldn't you say that that's correct? Pressure equals force over area. Yes? Now, good, excellent. Now, I'm going to give you the equation for pressure in a different form, okay? Pressure equals the Greek letter rho, lowercase, means density. How many people think of density as a D? Yeah, most of you, right? Actually, it's rho. It's not D. I don't know why. Who came up with D? D for density, I don't know. Okay? D is not density. It's rho. But we'll use D. Makes you feel comfortable. But I'm going to use rho for a moment. Is that okay? Okay. Rho GH. That's the density. Okay? The density of water times the acceleration due to gravity, okay, on Earth, and then the height of the fluid. Right? Is that okay? You get it?
Yeah.
Okay. So if I can make this equation look like this, am I right? If this equation can look like that, then it's true that the only thing that pressure is dependent upon is height, other than the nature of the liquid and the fact you're on planet Earth, correct? Is that okay? Yes or no? So I'm going to put this in a way that might be more familiar to you, okay? So we'll say pressure equals density times acceleration due to gravity times height, correct? What are the unit labels? What are the unit labels for density? Now, the physics ones, not the chemistry ones. The physics ones. We don't use centimeters, we don't use milliliters for volume. What's volume in physics? We only use, this is what we use in physics. Meters, kilograms, and seconds. I mean, we use other things, but in terms of this equation, that's all we really use. Newton, sorry. Newtons, which is really meters and seconds and kilograms. Yes? So what would density be, do you think? What would density be? Density is mass over volume, correct? So wouldn't it be true that density would be kilograms over meters cubed? Is that true? Right? Yes? If volume, if we only use meters, then it's going to be cubic volume, right? Red, are you with me? Okay? Right? So we're going to put in here, we're going to say pressure equals kilograms over meters cubed. Is that good? Are we all right with that? Now, what are the unit labels for acceleration? Meters per second squared. All right? Dot for times, is that okay? Meters per second squared. Okay? Is that good? Yes or no? I'm going to move this. You got to keep that, so I'm going to move that over here. Density GH. Okay, good. So now what's H? What are going to be the unit labels for a length? What is it? What is it? Meter. Yes. All right, let's see what we can do here. Let's manipulate this, okay? I'm going to keep this brief. All right? Well, does anybody see force anywhere here? Does anybody see force? Remember, we gotta find force and area. Does anybody see a force hidden here anywhere? Isn't force mass times acceleration? So isn't this force? Isn't it? Isn't that force? Neve, you with me? Yeah? Can I cancel that m with that m cubed? And what am I left with? Can I? In other words, m over m cubed equals what? Come on, guys, you can do this. Basic algebra. What is it? 1 over m squared, right? So I can get rid of that, and I can get rid of that and make that a 2, correct? Yes? So what am I left with? Aren't I left with newtons, right? Over m squared, which is force over area, which is there. Yes? You get it? You get it? Let me show you something really, 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 really cool. Okay? Old time dam. Old time dam. We're talking 100 years ago. This is what they used to do. You have a dam, right? Okay, here's the water, okay? And here's the land coming down, okay? This is all water, right? This is the dam, right? 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 And here's the city below. That kind of looks like an ice cap, doesn't it? Is that coming up on here? Okay, this is the city here. Okay, right? Are you with me? Thank you for paying attention, everyone. I appreciate that. So what happens is this. What happens if it rains? What happens if it rains and the water level goes up to here? Okay, but I don't want any water coming down on the stream. I don't want any water coming down here. What's going to happen? What's going to happen? All you need to do is take like a board, like a 2x10. That's all you need. And remember, this dam is only this wide. Let's say it's not very wide. Okay? All you need is like a 2x4, 2x10, put like that. Why is that true? Why? What's the pressure? What's the pressure is what? It's just right here. Like what's the pressure right there? Is it all of this? Now, we're assuming that there's not giant wave action and you got a lot of, you got a lot of pressure going this way. It's a completely calm day. Completely calm day. But what's the pressure here? What's the pressure down there? What's the pressure? It's just like that big, just 6 inches. It's hardly, is that a lot of pressure? No. No, what's an atmosphere, a whole atmosphere? You got to go down 30 feet. More than 30 feet, 10 meters, right? Yes? If you're scuba diving, anybody scuba diving here? Okay. What's the magic number? Anybody do serious scuba diving in here? What's the magic number when you're scuba diving? 30 feet. That's the magic number. Why 30 feet? It's essentially very close to, too close to, a second atmosphere. That's the magic number. You go down 60 feet, now you're going to have to start to worry. Yeah? So, 6 inches? It's 2 atmospheres. Pretty close to 2 atmospheres. Yeah, they do, but not on one. Yeah, but if you're going to go on one tank, you can't stay down very long because the pressure is pretty extraordinary at 60 feet. You can go 60 feet, but you're not going to stay down there very long. Okay. So that is, the pressure down there is not very high. Not very high. Why? Because it's just based on the depth. It's just based on the height of the water. Right? It's just based on the height of the water. Clear? Easy? Okay. Now let's talk about boiling. Let's talk about evaporation. Okay? What is the difference? This is now that you're a chemistry student, you have to understand the difference between these two terms. What's the difference? What are the differences between those two terms? Yes?
They're kind of like inverse each other.
One's very general, the other is much more specific. Yes?
Would evaporation be like when water is turned into a vapor and it's like going up towards like the clouds, and vaporization is just when it's heated to gas?
Isn't like evaporation just the surface?
Just surface.
Just the surface for evaporation.
Yeah. Vaporization is any water, anytime, any place, anywhere. That's vaporization. When something goes from the liquid state to the gaseous state. Okay? Evaporation is just at the surface. This is just surface. Okay? Just surface. Excuse me?
Anything more than surface turns into vaporization.
Yeah, well, I'm gonna explain that in a minute. I'm gonna make it a little bit more sensible. Okay? All right. Now, let's say we have water. Okay, we have the atmosphere up here. I'm just going to make that drawing is just going to be the atmosphere. Okay? All right, it's just going to be the atmosphere. And the atmosphere is going to apply what? A pressure, correct? Yes? So that's going to apply a pressure. going down, right? And we're going to call that P sub ATM. P sub ATM, correct? Okay, now. Now we're talking about room temperature. We're talking about a reasonable temperature. Okay, something where we live. All right. It's got to be the liquid state. Okay. Now, is this just at room temperature? Are you going to have evaporation occurring at the surface? Yeah, of course you are. In other words, if I left a glass of water and I came back a couple days later, what would happen to the water? It would have evaporated, or it would be less amount. Is that what you said? Yes, correct. Okay. So evaporation is occurring at room temperature, correct? Okay. Now we've got to go back a little bit to section 1. What causes pressure?
And when particles rebound.
Yeah, collision. Collisions. When molecules collide, that's pressure. Now, you only notice it really when they collide on the walls of a container, correct? You take a can of beans, unopened, and you put it on the stove. What's happening inside as you turn that heat up? What's happening inside? Yes?
Particles are moving around faster.
The particles are moving faster. And what's happening as a result of them moving faster? They're colliding with each other. If we all stood up and walked slowly around the room, we could easily avoid each other and have 0 collisions. Would that be correct? But if I said to run in any direction you want, as fast as you can, what's going to happen? You're going to have collisions. That's just the way it is. So your collisions are going to increase. What's kinetic energy? Energy of movement. The faster something is moving, the greater or the lesser amount of kinetic energy it has. The greater. Clear? What has greater kinetic energy? Gas or liquid? A gallon of water at room temperature, a liter of water at room temperature, or a liter of water at 100 degrees Celsius. What has more kinetic energy? Yeah, the liter of water at 100 degrees Celsius. What has greater kinetic energy? A cup of tea in a small mug, or the Atlantic Ocean? The Atlantic Ocean. Clear? Okay. Now,
How big is the mug?
small mug. I can pick it up with one hand.
Alright, never mind.
Typical standard mug. Okay? Now, so if I turn this heat up, what's going to be given off to a greater extent? I'm going to increase the rate of evaporation. I'm going to increase the amount of particles that it gives off, correct?
Yes.
So what am I increasing? If I'm increasing the number of particles, what am I increasing as a result of increasing the number of particles in the air? I'm increasing kinetic energy. I'm increasing pressure. And what do you call that pressure? What do you call that pressure? Now, this is the atmospheric pressure, Aaron. We've already stated that. We've stated that that's the atmospheric pressure. This pressure is called the vapor pressure. Do you understand that? Now, so now we know where vapor pressure comes from, correct? Yes or no? Let me ask you a question. A volatile liquid such as alcohol will have a lower vapor pressure than water. Boy, I threw some words in there that you may have no idea of. How many people have ever heard of rubbing alcohol that you put on your skin or a wound or something of that nature? Okay, good. Can you smell it?
Yes.
Does it evaporate really quickly? Yes or no? And I'm asking you to guess because of your experience. You do, are you aliens? You've been here your whole life. You've seen alcohol. You've smelt it. Let's say alcohol, for those of you who have heard of alcohol, and I'll give you something similar to alcohol for those of you who haven't heard of alcohol, but have done nail polish removal, called acetone. Isn't alcohol and acetone similar in terms of it evaporates quickly, smells terrible, and could essentially light on fire, but we're going to ignore the chemical properties of each. So, would you say, yes or no, that alcohol and acetone evaporate to a much greater extent than water at the same temperature?
Yes.
Would you say that's true? Therefore, is the vapor pressure of water greater or less than the vapor pressure of acetone and alcohol at the same temperature, same quantity, everything? In other words, if I say to you, this is A, this is ethyl alcohol, rubbing alcohol, okay? You may think rubbing alcohol is like isopropyl alcohol. It doesn't matter. It's medicinal use, not for drinking. Okay, good. And this is acetone. Okay? And this is water. Okay? A, B, and C. Okay? Would you say which one is going to have the lowest vapor pressure?
C.
At the same temperature? C, water. Why? 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 Lulu? Why? Well, have you ever seen alcohol? Or you may never have seen it, and that's an okay thing, okay? These things evaporate very quickly. If I had three containers, same volume, these two are going to be gone very quickly, okay? Look up someone, Salmon, on your computer. Mohammed, what is it that you're doing? Should I check the history? I don't think so. Close your computer, please. Thank you. Quickly. Look up vapor pressure of acetone, vapor pressure of ethyl alcohol. Ethyl. Ethyl alcohol, or ethanol, depending. This is going to be acetone.
It's 5.95.
All right, same unit label. So we're going to say, we don't need to know the unit labels, but we'll say, what is this one?
5.95. No, for yeah, ethyl alcohol.
5.95. What's acetone?
It's not here.
We need the same unit labels. Otherwise, we won't know what they are.
I can't find it.
Okay, somebody else. There are a million. All right, I will let you alone, but you've got to find all three on the same table. Okay, thank you, Aaron, for paying attention. It really does a lot for me. Excellent. I appreciate that. Excellent. Practice juggling outside of school. Excellent. So, these have much greater vapor pressure than these. Would you say that's true? Yes or no? Okay, good. Now, when the vapor pressure equals the atmospheric at room temperature, it doesn't matter. I don't care. Just it doesn't matter as long as they're all the same unit labels and they're the same conditions. I don't care. I just want to compare one with the other. But please don't call out unless I call on you, okay? Because we only got like 30 seconds left, okay? All right, so where these are equal, okay, when the vapor pressure equals the atmospheric pressure, that's called boiling. And the vaporization can take place anywhere in the liquid, anywhere. The vaporization can take place anywhere in the liquid and it just goes crazy. The bubbles form. Okay, understood? And I will do another video on this which will explain it a little bit more. Let me ask you one question and then we're done. Mountains, the Alps, the Rocky Mountains, Mount Everest, Nepal. Is the atmospheric pressure in those areas greater than or less than Abu Dhabi? The atmospheric pressure in mountains is greater than the atmospheric pressure in Abu Dhabi. Is that what you're saying?
No, it's less pressure.
It's less pressure. It's less pressure in the mountains, correct? The atmospheric pressure, Alec, have a seat, thank you very much, is much less in the mountains, correct? Okay. Would the vapor pressure have to be higher or lower, therefore, in order for boiling to be achieved? It would be lower. Understood? So would boiling occur at a lower temperature or a higher temperature in the mountains? A lower temperature. Have a great lunch.